Hello everybody, welcome to your topic 1 Ticket to Reteach video. We're going to run through all these problems together, so just please take notes, make any side notes if you hear anything helpful, and we will make sure that this material we are understanding. So for items 1 and 2, identify the following information for the function of each graph. So domain is your input values, it is the x values. Here's our graph. It's going to continue forever up but also out. This is going to continue forever up and out. This graph will hit every single x value, which means our domain will go interval notation, smallest number first, negative infinity to positive infinity. And these get parentheses because you can't actually include infinity, but you will approach infinity with that domain. Okay, our range is going to be y values. How far down does our graph get? How far up does our graph get? Start with the smallest value. So going down is the smallest value. So I can see right here at negative 25 is our smallest value. And it's going to go all the way up to, how high is this going to get? Well, with those arrows, it's going to continue forever up to a positive infinity. Parenthesis with the infinity, but this 25, this negative 25 is on our graph, so we are going to include that. We indicate that negative 25 is part of the range with a bracket. Okay, X-Intercepts, where is the graph crossing the x-axis? So I'm crossing right here and right here. That's at a negative 5 and a positive 5. The Y-intercept is where is our graph crossing the y-axis. That's at that negative 25 that we saw before. Okay, so now it gets into the trickier things. Interval positive. Where is our graph positive? Your graph is positive above the x-axis. So here's our x-axis. Anything above that, our graph is positive. So what are those intervals? Intervals go from the smallest number on the left to the largest number on the right. So this portion of our graph is going to get an interval, and this portion of our graph is going to get an interval. So this portion right here, the smallest number is going to be the furthest to the left. So if this is going to continue forever out, our smallest value is a negative infinity. And it's going to go all the way to, and again, we have our graph here, all the way to this x value, so from negative infinity all the way to a negative 5, that's where our graph is going to be positive above the x-axis. Parenthesis on the negative infinity, and then that negative 5 is that point where it switches between positive and negative, so we are going to have a parenthesis there. And we have another positive interval over here. So smallest number first, largest value second. Where does our positive interval start? The smallest value here is at a positive 5. And it is going to continue forever to the right, so that will continue forever to positive infinity. Parentheses on both of those, because we always have a parenthesis with infinity. And this 5 is on the x-axis. It's in between positive and negative intervals, so we just we do not include that. It's not positive or negative. All right, a negative interval is where is your function below the x-axis. So we've got this portion of our graph that is below the x-axis. From here all the way to here, so from negative 5 to positive 5, our entire function is below the x-axis. Using interval notation, where we've got negative 5 as our smallest value all the way to a positive 5, but we're not including those values because that's on the axis where it's in between the positive and the negative. But from here to here, the whole function is below the x-axis. All right, where is our interval increasing and decreasing? So increasing is going to look like that. Decreasing is going to look like that. So we're increasing, right here is our point where it changes. We're increasing, there's an increase right there. So what is the interval notation for that? Well, it starts at the x value of 0, and everything to the right, we are going to increase that whole way. So our increasing interval starts at 0 and goes to positive infinity. And again, that 0 is when it switches between increasing and decreasing. So we're going to have parentheses not including those. The decreasing, we have a decreasing interval over on this side. It's decreasing. So again, here's that point at 0 where it switches between decreasing and increasing. So what are all the x values on this side? Because that's all the x values on this side where it's decreasing from left to right. So the smallest x value goes first at negative infinity, positive, or all the way to the biggest x value, which would be a 0. That's when it stopped decreasing and then it switched to increasing. Okay, we have average rate of change. Anytime you see average rate of change, you're going to find the slope. You can do this two ways. We're going to find the slope over the interval from -5 to 0. We want to remember that those are both x values. So -5 is right here, and 0 is right here, but I need to go down to where the function is, right there. So that's where 0 is. And we want to find the slope of the straight line that would connect those two. So those two ordered pairs, one of them is -5, 0. The other ordered pair is 0, -25. Again, I just found this interval from -5 to 0 and found what those points correspond to on the graph. And now we just find our slope. Slope formula is y2 minus y1, x2 minus x1, so minus a -5 turns positive, and we get a -25 over 5, which reduces to an average rate of change of -5. All right, so we're going to review all those concepts one more time. This was, I believe, among the more challenging parts of this chapter. So for number 2, domain, think x values. Here's we have a v, it's going to continue forever this direction and forever in the other direction. So every single x value will be part of our domain. So that means from -infinity to +infinity, we have our domain. Our range is the y values. What's the smallest y value? Well, our graph goes all the way down to here. That y value is a 3, and it's going to continue forever going up. So our range starts at 3, the smallest value, and it's going to go all the way to +infinity. Parenthesis with +infinity, that 3 right here is part of our graph, so we're going to include that in the range, so we do a bracket on the 3. All right, X-intercepts, where is our v crossing the x-axis? It's not, so we are going to say there are none. No x-intercepts. All right, y-intercept, where are we crossing the y-axis? Up there at a +7. All right, interval where our function is positive. Remember, positive means above the x-axis. Well, the whole thing is above the x-axis. And we're going to focus on the interval of the x values. So all the x values going to the left, all the x values going to the right. All of those x values, you have a positive interval. So from -infinity all the way to +infinity. Where is our function negative? Negative is below the x-axis. This graph will never go below the x-axis, so we don't have one. So we're going to say none on that. Okay, increasing or decreasing? Where is our function increasing? Remember, increasing is going to look like this. Decreasing is going to be going down. So we can see, oh yeah, we're increasing right here. What is the interval of x values where that's happening? So I drew a line straight down. I can see that it starts increasing at -2, and it's going to increase all the way to the right to a +infinity. That -2 is the point where it switches between increasing and decreasing, so we're not going to include it. Okay, where is our graph decreasing? Well, decreasing is going down like this. From left to right, we have what would be considered a negative slope, but it stops right here and switches to increasing. So we need all the x values on that side of that -2. Well, the smallest x value all the way to the left is going to be a -infinity, all the way to the biggest x value of -2 before it switches to an increasing interval. Okay. Oops. Average rate of change. Remember, average rate of change is slope, and the interval they're giving us are x value intervals. So if you go to -2 for your x and go up to your function up here, and then if you go to 0 for your x but go up to where your function is, which is up there, we want to find the slope between those 2 points. Sometimes if it's really clear, you can just count the rise over the run. If you start on the point on the left, we're going up 1, 2, 3, 4, and we're running 1, 2, so our slope would be 4 over 2, or we have an average slope or average rate of change of 2. All right, number 3. All right, so we have Ching is filling a 50-foot cube container of water at a rate of 0.5 feet cubed per minute. Interpret the key features of the situation. So key features are not too bad to do. That's what we just did on the 2 problems above, but if we have a visual for this. So if we think about what's happening, our visual would be Ching is filling a 50-foot cube container with water. So at the start of our time, we don't have any water in this container. So we're down here at 0. Chang is going to continually fill this up at a steady rate at 0.5 feet cubed per minute until we get it full. When it's full, that's at 50 cubic feet. So the rate that that's happening is half a cubic foot per meter. And how many halves are in 50? That's going to tell us how long that takes. There are 100 halves in 50, so this will take 100 minutes for this to happen. So interpret key features. We'll just do a few of them and move on. But we could talk about the domain and range. So domain from here to here, those are those x values from 0 to 100. So our domain, smallest number first, largest number second, and 0 and 100 are part of the domain, so those are going to get brackets. The range is your y values. So from here to here, 0 to 50 is our range. And those values are part of our function, so those will be included. Let's see, domain, range. I think we're going to call it good there with domain and range. For a problem similar to this, I think understanding a visual and then you can answer a domain and range question makes that helpful. All right, number 4. Graph the function g of x equals absolute value of x plus 4 as a translation of the parent function f shown. So here's our parent function. Your parent function of absolute value of x is at the origin for the vertex, and it has that up 1 over 1 pattern. Up 1 over 1, up 1 over 1, up 1 over 1. So how does a transformation affect, or if we were to graph absolute value of x plus 4, what does that do? So that plus 4 is going to shift our graph up 4 units. It's not shifting left or right at all. There's not x plus or minus a number inside. So we are just going to shift up 4 units, up 4, and then we can plot our graph. There was not a stretch or a compression, so you still have that up 1 over 1 pattern. So how did this affect the domain and range? Well, the domain of absolute value of x, let's see, f of x, here's our parent function. That domain is all the x's to the right, all the x's to the left, so all real numbers from -infinity to positive infinity. So the domain of our new function, g of x, that didn't change. Moving the graph up 4 didn't change the domain, so our domain is still -infinity to positive infinity. This function will still go all the way to the right and all the way to the left, hitting all of those x's. the range of our original parent function, here's our v, it's going up above that 0 line, and there's nothing below it. So the range, I'll write this one out. The range started at 0 and went all the way to positive infinity, and that 0 was part of our range. So if we move this graph up 4 units, 1, 2, 3, 4, that is changing the range. So it is going to have an effect on the range because our range no longer starts at 0, because this red graph is not below that 4 mark at all. We don't have any v down there. So our range now starts at 4 as the smallest value, and it's going to continue up to a positive infinity because it will continue forever going up this way, hitting every single y value. That 4 is included, so it's going to get a bracket. Okay, for items 5 and 6, what is the equation for each reflected graph of f of x equals x squared minus 4? So any reflection questions, we do have to pay attention to which axis are we reflecting across. When you reflect across the x-axis, our new function, maybe I'll call it g of x, there's a negative involved. The negative goes out in front. So a negative x squared minus 4. That can't simplify beyond that at all, so that's what reflecting across the x-axis would look like. When you reflect across the y-axis, where does the negative go? So our new function, the negative has to go inside with the x. So I'm going to create an inside with the x like that, so I can put a negative right there. And then we've got our squared minus 4. So the main thing we want to remember, if it's x-axis reflection, negative just goes out in front. If it's a y-axis reflection, the negative has to go inside of either parentheses, or if you were dealing with absolute value, it would go, like if you had the absolute value of x, it would go inside with the x. That would be a reflection across the y-axis. In this case, we actually can simplify. A negative x squared is a negative x times negative x, which does turn to a positive x squared minus 4. And so that would be our reflected graph right there. Okay, I do need to clarify one thing. With the reflecting across the x-axis, the negative that goes out in front, I apologize for not doing this. You do have to put it in front of the function. So I'm going to throw parentheses around the function, and that negative is now out in front of the function. So then that can be simplified to a negative x squared plus 4. But again, where does the negative go with each reflection? That's the thing we have to keep straight. All right, we're going to practice some graphing. Graph each function as a vertical stretch or compression of the parent function. So here is the parent function with the pattern up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. If we multiply out front by a 4.5, that is a stretch. That up 1 over 1 pattern, we're going to multiply the top by a 4.5. So now our pattern is up 4.5 over 1, and we would just continue that over and over. So up 4.5 over 1 puts us there. Up 4.5, 1, 2, 3, 4, it's going to put us somewhere up there. We'll get the same points on the other side, up 4.5 over 1, and this was a stretch. You can see how our V got more narrow. Okay. How do we graph something that has a 0.5 out front? Anything that is between 0 and 1, the absolute value of it is between 0 and 1, is going to be a compression. But we know we have a 1, 3, 5 pattern for parabolas. Whatever this is out front, which is our A value, we're going to multiply that by the 1, 3, 5. So 0.5 times 1, 0.5 times 3, 0.5 times 5. Half of 1 is 1/2. half of 3 is 1.5, and half of 5 is 2.5. So our graphing pattern is now 0.5 over 1, 1.5 over 1, 2.5 over 1. So from the origin, we would go up a half and to the right 1. Then you would go up 1.5 to the right 1, then up 2.5 to the right 1. You can see it looks like that is widening our parabola. That's what a compression will look like. Our vertex did not change, so here is our new function. All right, 9 and 10. What transformations of f of x equals x squared are applied to get our new function? So any number out in front will be a stretch or a compression. If that number is bigger than 1, that is a stretch by a factor of 3. That's how we would say that. All right, any number inside with the x will be a translation to the right or left. Remember, tricky x, so we would translate to the left 2 units. And those are the only transformations for that function. Number 10, we have a negative out in front. That's a reflection. When it's out in front, it's a reflection across the x-axis. X minus 5 is going to be a translation to the right, tricky x. So we're going to translate to the right 5 units. This plus 1, we're going to translate up or down with that. That positive 1 means we are going to translate up 1 unit. All right, so number 11, given the parent function f of x equals x squared, what is the new equation if the function is translated 4 units to the right and 3 units down? So we're going to take our x squared, and translating 4 units to the right is going to shift your x's. That's a horizontal translation. So remember, it's tricky x. Normally to the right we would say x plus 4, but because it's tricky, we need to say x minus 4. The squared goes on the outside of that, and then to go 3 units down, we just subtract 3 off on the end. All right, everybody's favorite piecewise functions. I noticed there are a couple of open circles. I don't know yet if that's going to come into play with what we're doing, but we're just going to ignore those for now and see if we end up using those circles. But piecewise graph is you're going to graph a piece of this function and a piece of this function and a piece of this function. If it makes it easier to do this, feel free to write those functions off on the side. If it's just a 2, that's y equals 2. Y equals 2 is just a horizontal line going through the y-axis at 2. So I know I'm going to have this horizontal line right here. Then what I pay attention to is what part of that line do we want? We want that line from a -4 to a -2 for those x values. So I'm going to go ahead and draw a vertical line at -4 and a vertical line at -2. And I want that line y equals 2 in that interval, just between those two lines. So y equals 2, like we said, is horizontal. That's the piece of that line that we want. And then it's going to have open or closed circles. Where it hits the -4 has a less than or equal to, that's a closed circle. Where it hits the -2 has that less than or equal to, that's a closed circle. All right, our second function is x plus 2. So that's just y equals x plus 2. And we want to graph that line over this interval, just from a -2 to a +3. I already have a vertical line at -2, so I'm going to go ahead and draw a vertical line at +3. and we want the line y equals 2 in between those two lines, or y equals x plus 2, excuse me, in between those two lines. So what's helpful here is we have our y-axis within this interval, so I can just go, the y-intercept of that equation is positive 2, the slope is 1, so up 1 to the right 1. I'm going to backtrack, I'm going to draw that line in, and then determine if I want open or closed circles on either end. It says negative 2 is less than x, so that will be an open circle. Now I see why they gave us that open circle there. X is less than 3, that is another open circle where it hits the 3. And there's the piece of that line. All right, our last function is y equals negative 3x plus 12. And we want to graph that line just between 3 and 5. We already have our line at 3, so we're going to go ahead and create a line at 5. Now here's where this gets challenging because my y-intercept is 12, my y-axis is over here in this other interval, and 12 is way off my graph. If I can figure out where to start my line, so where this x is a 3 is this vertical line right here. If I can find the y value that goes with that 3 from this line, then I've got a starting point, and because we know the slope is negative 3, we can get the rest of the line from that. So I'm just going to plug in a positive 3 to the function. Y equals negative 3 times 3 plus 12. Negative 9 plus 12 is positive 3. So I know this ordered pair 3, 3 is on this line that I have to graph. So I'm going to go over 3, up 3. I'll plot the point. I'll come back to figure out if that will be an open or closed circle. I thought I already drew this line, and here's this vertical line, 3 to 5. So now we have a slope of negative 3. So from that point, I'm going to go down 3 to the right 1, down 3 to the right 1. Here's our line in this interval from 3 to 5, and I can see 3 is less than or equal to, so that's going to be a closed circle to start the line. X is less than or equal to 5, so closed circle to close that line. All right, our next example, now we're going to write our own rule that defines the piecewise defined function in the graph. So let's identify those boundaries, those vertical boundaries that we had in our last one. I can see we have one here. That's where the end of one piece of a graph is and the next one starts. And I can see we have one here. So I'm going to need a function for that, or I'm going to need an equation for that function, an equation for that function. So f of x equals, I'm going to have two lines because there are two functions that we're going to write an equation for. So our first one is this one on the left, horizontal line. Anytime you have a horizontal line, it just has the equation y equals whatever that number is, wherever you're crossing the y-axis. Our y-axis is counting by 2's. We want to be aware of that, so it is crossing at 6. So in our piecewise function, 6 is our first function, but for what interval? What values of x do we have this line? Well, here's our cutoff. It's at a 0 for the x, and it's everything to the left. Everything to the left is going to be less than. So our function is equal to 6 for all the x's that are less than 0. And I said less than instead of less than or equal to because this is a closed circle when x is a 0. So our intervals off on the side, we do have to just look at the x-axis to determine for which x's do we have our function equal to 6. Okay, our second function is from here to here. It's a line. If we can identify the slope in the y-intercept, we can write an equation for this. Your slope, if you can just find 2 exact points to count the rise over the run. So here's one, maybe I'll count from here. Where we need to be careful on this is that our axes are counting differently. Our y-axis is counting by 2's. So when I count the rise, I'm going 2, 4, 6, 8. So my rise is 8, and the run, my x-axis is counting by ones, 1, 1. So I'm going to run to the right, 1, 2. So our slope is rise over run, 8 over 2, which is 4. Then we want to try to find the y-intercept. So where is our line hitting the y-axis? That's happening down here. Remember that y-axis is counting by 2's. So -2, -4, -6. So our y-intercept, which is the b value of y equals mx plus b, is a -6. So we can write our equation. Y equals, the slope was positive 4x, the y-intercept was -6. So we've got our equation. F of x equals takes care of our y equals. So 4x minus 6. And then for what intervals of x do we have that line? So that's just saying between these two vertical lines from 0 all the way to 4, that's the piece of that function that we want. So we're going to go from 0 to 4. So 0 is less than, and then I have to look to see if it has an open or closed circle at 0. So at the 0 line, we have a closed circle. So 0 is less than or equal to x, which is less than, and then I look to see if it has an open or closed circle. When it hits the line at 4, that's closed. So it's going to be less than or equal to 4. And that takes care of our piecewise function. Okay, using a graph to solve an equation. The equation is x minus 3 squared minus 1 equals 3. We are going to break this up into two equations. First one is the left side of our equal sign. Y equals x minus 3 squared minus 1. The right side is y equals 3. We're going to graph both of these functions, and we're going to see where do the two functions intersect. So the first one, this is an x squared, so it's a parabola. Tricky x, we have a shift to the right 3 and down 1. So I can go ahead and go to the right 3, down 1. That's going to be the vertex of my parabola. We've been working a lot with our a value. Our a value is 1, so 1 times 1, 3, 5. We have a 1, 3, 5 pattern. So that means from that point, you can go up 1 to the right 1, plot a point, up 3 to the right 1, and up 5, 2, 3, 4, 5, to the right 1. Let's get those same points on the other side. And we can go ahead and draw in our parabola. We also need to draw this second line, y equals 3. Anytime it's y equals a number, it's just a horizontal line that crosses the y-axis at 3. So here's our horizontal line. And then I'm looking for any intersection points. So what's kind of nice here is we have two intersection points, and they intersected at an exact point. I plotted those points while doing the 1, 3, 5 pattern, so I know those are exact values. Now, when we solve the equation, all we care about are the x values of those 2 points. So if I go to the point and go straight down to the x-axis, I can see that x is equal to a 1. Find the other intersection point, go straight down to the x-axis, x is also equal to a 5. So even though these are ordered pairs where their two functions intersect, it's the x value of the ordered pair that gives us our solution over here. All right, using a graph to solve each inequality. So last chapter, when we had an x squared plus 4x minus 5, so let me start over. We're going to graph two functions. We're going to graph the left side, y equals x squared plus 4x minus 5. We're going to graph the right side, y equals 0, and we're going to see when is this function less than this function. Last chapter, we didn't do much at all with quadratic functions that have this 4x in the middle. So my advice to you was to graph it on your graphing calculator real quick so you can identify the vertex. When that's graphed on the graphing calculator, the vertex we can see is at a -2, -9. Once you know where the vertex is, you can use your 1, 3, 5 pattern. Our A value is 1, so 1 times 1, 3, and 5 is just 1, 3, 5. So if we plot that point, -2, -9 is down here. Let's do our 1, 3, 5 pattern. So up 1 to the right 1, up 3 to the right 1, up 5 to the right 1. And then let's get the same points on the other side. We can sketch in our parabola right here. Our second function is y equals 0, so we can draw just that horizontal line at 0. And the question is, when is the parabola less than the horizontal line y equals 0? So what that looks like on a graph is, here's our horizontal line. Where is the parabola less than that? All of this down here. Here's where your parabola is less than. So it's this continuous part of the parabola, but again, because it's a solving for x type of problem, we only care about the x's. So from here to here, that's when the parabola is less than that horizontal line at 0. So from -5 is less than x is less than +1. Here's from -5 to 1. Our function between these two values is below that y equals 0 line. So this is an answer to solving that inequality. Okay, so use graphing technology to approximate the solutions of the equation to the nearest tenth. I'm going to throw in a video here on the graphing technology so that you can see how that works. One thing I want to point out is, you notice we have x squared plus 5x minus 2 on one side of the equal sign, 6 plus 3x plus 1 on the other side of the equal sign. So that's going to be our two separate equations. We are going to say y equals the first side, y equals the second side, and then we'll see how to do this graphing. All right, so we're going to use graphing technology to solve the equation. We go to our y equals and type in x squared plus 5x minus 2. Our second equation, 6 plus the absolute value. We hit math, we arrow over to number, hit absolute value of 3x plus 1. All right, I'm going to hit graph. We've got our parabola. We've got our absolute value. I can see that they're not crossing on my graph, so I need to zoom out. I'm going to hit zoom. Let's zoom out a little bit. I need a better picture of this. I'm going to move my cursor. Where do I want to zoom out from? Over here somewhere. Let's just zoom out and see if we can get a better picture of what's happening. Okay, now I can see there are two intersection points, so I want my calculator to calculate those intersection points. So above trace you have the calc, so we hit second calc. I want it to calculate the intersection, so I need option 5. Right now it's on the blue parabola. I always start on the left. I'm going to go to the left, and I estimate this is where they're intersecting. It puts my cursor on the red V, absolute value, so I'm going to estimate, I think that's where it's crossing. And then what is my guess for the intersection point? Right there, and I can see it's intersecting at -8.79. So I'll just round that to -8.8. Remember, your solution is the x value, not the y value of these intersection points. Okay, so I want to do that again, but with the other intersection point. So I'm going to ask my calculator to calculate this again. So I hit second calc. I want to find another intersection point, so option 5. I'm on the blue parabola. I'm going to go over to where that looks about where it's intersecting to me. It is putting the cursor on the red V, so where does it seem to be intersecting? Maybe about there. And what's my guess? My best guess is, I don't know, maybe right there. It's going to calculate and give me the intersection point at 2.12. So I will round that to the nearest tenth, 2.2. Again, it's the x value that is our solution, not the y value. All right, so let's move on to number 17 and 18, solving a system of equations in two variables. We did a lot of elimination with these during class, so I'm just going to stick with that. That'll probably be pretty familiar to you. With elimination, you want to make sure everything's lined up. So your x's are lined up, your y's are lined up, your equal sign also has to be lined up, and then we've got these numbers on the end. So we're ready to go. We're trying to see if anything will eliminate when the equations are added together. Right now, 4x plus negative x equals 3x did not eliminate. 3y plus y is 4y did not eliminate. So what we do is we bring in multiplication to manipulate our equations to get something to eliminate. So I would like to eliminate this 4x right here, or the x's. So if this is a 4x, below this, I want this to be a negative 4x, because 4x plus negative 4x equals 0, and I get to cross them off. So to make that happen, I'm going to multiply the entire equation by a 4, because I can see that 4 times negative x will give me a negative 4x, which will cancel with our 4x on the top. The top equation we did not need to change, so I'm just going to carry that down. 4x plus 3y equals negative 16. I'm going to distribute that negative 4, and I'm going to be careful to distribute to every single term. So negative 4x plus 4y equals positive 16. All right, so now I'm going to add the two equations together. When I add the equations together, I want the x's to eliminate, so 4x plus negative 4x cancels. That equals 0. Then I have 3y plus 4y equals 7y. And then over here, this throws people off sometimes. Here's negative 16 plus 16. So, hey, they cancel. We'll cross them out. But I still have an equation down here. I need to write something on that side of the equal sign, so I'm going to put a 0 over there. Don't let that 0 throw you off. We still have a variable, which means there's still solving to do. We can go ahead and divide both sides by 7 to get the y alone. So our y value is equal to 0 divided by 7 is 0. So our solution is going to be an ordered pair. We just figured out that the y value, the second half of it, is a 0. Now to get the x, we're just going to take that 0. I can plug it in for the y up top, or the y in the bottom equation, whatever one feels easier. I'm leaning toward that bottom equation. It looks simple. It's just a negative x plus y equals 4. But now that we know that y is a 0, I'm going to replace the y with a 0 and solve for x. Negative x plus 0 is just negative x equals 4. That negative is like a negative 1, so I want to divide both sides by negative 1, and we get x equals negative 4. So we just found the x value of our equation, and we have solved our system of equation using a process called elimination. All right, number 18, same idea. Let's solve using elimination if everything is lined up. Our x's are lined up, our y's are lined up, and our equal sign is lined up. We want to get either the x's or the y's to eliminate. I'm leaning toward the y's right here. I can see I have a negative 4y up here. If this was a positive 4y down here, I could get that to eliminate. So it's already a negative y. To get it to be a positive 4y, I'm going to multiply by a negative 4. Because negative 4 times negative 1 is positive 4y. Plus this negative 4y, that's going to get that to cancel. Sometimes you do multiply the top equation by a value. It's not the bottom equation every time. That's just how it happened to work out on this one. So our top equation was good to go. 2x minus 4y equals negative 4. The bottom equation, we're going to multiply that negative 4 through the whole thing. So negative 12x, negative 4 times negative y is positive 4y, and negative 4 times 4 is negative 16. We're going to add our two equations together. So 2x plus negative 12x, that's a negative 10x. Our 4y's cancel, negative 4y plus 4y. And then negative 4 plus negative 16 is a negative 20. We have an equation with an x to solve for, so let's keep solving. We're going to divide both sides by negative 10. And we get x equals negative 20 divided by negative 10 is a positive 2. So our solution, we have the x value. To get the y, we're just going to plug in a 2 for either the x in the top equation or an x in the bottom equation, whatever you prefer. I feel like the bottom equation looks a little bit easier, so I'm going to do 3 times, instead of x, I'm going to replace that with a 2, minus y equals 4. 3 times 2 is 6, minus y equals 4. That 6 is a positive 6, so we'll subtract 6 from both sides. Carry down a negative y equals negative 2. That is a negative 1y. Divide both sides by negative 1. And y is equal to a positive 2. All right, moving on to the last page. Solve the system. This is a system of equations in 3 variables, which is why there are 3 equations. What we need to notice is that only one of the equations has all 3 variables, x, y, and z. The first equation is missing the z. The bottom equation is missing the y. We want to fill in those missing variables with a 0, like a 0 z or a 0 y. So I'm going to rewrite the system. The top equation, we have 2x plus 5y. We're missing the z, so I'm going to say plus 0 times z, because 0 times z is 0, which is why there's nothing there, equals 13. But that just gives me a placeholder for my z's. Second equation looks good. We have all 3 variables, negative 3x plus y plus 2z equals 6. Bottom equation, we're missing the y, so we have 4x. We're going to plug in a 0y for that spot, minus 3z equals positive 5. Okay, we are going to solve their system of equations by eliminating either the x's, the y's, or the z's. You know, whatever one just feels easier. And just to be safe, let's eliminate the variable first where we have all 3 of them in the equation. So let's work on getting rid of these x's, and then we can solve our system after that. So if I pair up really any combination of equations, maybe I'll start with just the first 2. If I'm trying to eliminate the x's, this is a negative 3x, this is a positive 2x. I want those to be the same number with opposite signs. So I can multiply those up to 6's, positive 6, negative 6. So if I take this top equation, multiply it by a 3, the bottom equation, multiply it by a 2, that's going to give me a 6x up here and a negative 6x down there, and those will eliminate. So I'm going to rewrite those equations, multiplying the 3 and the 2 through the whole thing. So our new equation for the first one becomes 6x plus 15y plus 3 times 0 is still 0, so 0z equals 39. Our second equation, multiplying a 2 through that whole equation, is negative 6x plus 2y plus 4z equals 12. We're going to add these 2 equations together. When we add these together, our x's eliminate as we had intended. We have 15y plus 2y is 17y plus 0z plus 4z is still just a 4z. And then 39 plus 12 is 51. We're going to circle that equation because we're going to come back to it. We want another equation with just a y and a z. So we have to eliminate x again. So I go back to the original equations. Maybe I'll get rid of some of my notes here where we had worked with the first 2. That's a 3. I just kind of erased. All right. So we need to eliminate the x again. We worked with the first two equations on that. Now I could work with the first and the third, or the second and the third. I'm going to go with the first and the third. Looking at the x's, this is a 2x, that's a 4x. If I can make this top one a negative 4x, those would cancel. So I'm going to multiply the top equation by negative 2 and rewrite that down below. We have negative 4x minus 10y. Negative 2 times 0 is still just 0, z, equals negative 26. Now the third equation we didn't need to change, so I'm just going to carry that down. 4x plus 0y minus 3z equals 5. Let's add our two equations together. Our x's cancel like we wanted them to. Negative 10y plus 0y is negative 10y. 0z plus a negative 3z is negative 3z. And negative 26 plus 5 is negative 21. Circle this equation. We've got our second equation with a y and a z. Here's a y and a z. And so we are going to bring these two equations together. For one final system, we have negative 10y minus 3z equals negative 21. 17y plus 4z equals 51. We're going to take a look at both of our variables and figure out, does the x or the y, does the y or the z seem easier to eliminate? I think the z's do. That's just a negative 3 and a 4. We can multiply those both up to a 12, positive 12 and negative 12. So this top equation, it's a negative 3z. I'm going to multiply that by 4. The bottom equation has a positive 4z. I'm going to multiply that by 3, and that's going to get us ready to eliminate the z's. So I multiply the 4 through the top equation. We have negative 40y minus 12z equals negative 84. We're going to multiply 3 through the bottom equation. 3 times 17y is 51y. 3 times 4z is 12z. And 3 times 51 is 153. We're going to add these two equations together and really hope that we get a nice answer out of this. All right, negative 40y plus 51y is a positive 11y. Our z's cancel. We designed that to happen. Negative 84 plus 153 is 69. Okay, so in all honesty, I got that answer and thought I had made a mistake somewhere. So I went back, checked an answer key. I probably should have checked what the final answer was before I chose this problem. These are decimal answers. There have been no mistake in the work so far, so we're just going to keep solving. We're almost done. We've done a lot of work, so we will just work with some decimals. So our y value, if you divide that in a calculator, you get 6.27 repeating. So we'll just say 6.27. We'll round to 2 decimal places. All right, so we got our y. Once you have one variable, to get any other variable, you're just going to go back one step. So I want to go back to an equation that has a y and only one other variable. I can choose this equation right here, or I can choose this equation right there. Maybe I'll choose this one over here because I have a little bit of space below to work on that. So I'm going to plug in 6.27 for the y, which will allow me to solve for z. So negative 10 times 6.27 minus 3z equals 21. Let's figure out what negative 10 times 6.27 is. It's going to be a negative 62.7 minus 3z equals 21. We'll add 62.7 to both sides. Negative 3z equals 83.7. If you divide both sides of your equation by a negative 3, our z answer or value is negative 27 0.9. All right, so we have our z, we have our y. To get the x, we have to go all the way back to an equation that has an x, which would be one of these starting equations. Honestly, any of these that you want to plug into is fine. Maybe I'll pick this bottom one, this 4x plus 0y minus 3z. So our equation is 4x, so 4, we don't know the x, plus 0 times, I don't really need to plug in the 6.27 because 0 times anything is 0, but I will, minus 3 times negative 27.9 equals 5. Okay, so 4x, 0 times 6.27 cancels, negative 3 times negative 27.9 is a positive 83.7 equals 5. Subtract 83.7 from both sides. So 4x equals whatever 5 minus 83.7 is, which is negative 78.7. Divide both sides by 4, and we get our x value of negative 19.675. We were rounding to the nearest hundredth, so I'll just say negative 19.68. All right, so final solution. An ordered triple, we have our x of negative 19.68. We have our y of 6.27, and we have our z of negative 27.9. Again, the decimals threw me off for a second, but all the work we did to get there is good steps to follow. And then once you get one of the answers, you just start plugging in, moving backwards to find the rest of your solutions. All right, our last two problems are kind of similar. These are the examples where you are creating a system of two equations, which means you only need two variables, with a no solution answer and an infinite solution answer. So we just went through a bunch of eliminations, so we can approach this with elimination again. Let's say I just keep it simple. X plus y equals something. Now, to get a no solution or infinite solution answer, you need your x's to cancel and the y's to cancel. So my x's would cancel if this was a negative x below it. The y's would cancel if this is a negative y below it. And now to get a no solution answer, I need, so let's think through if I were to add these two together, x's would cancel, y's would be cancel. I'd be left with 0 equals. I need something over on this side that is not equal to 0 when I add it together, because I need this to be a false statement. So maybe this equation on top is equal to a 1. The equation on the bottom is equal to a 2. 1 plus 2 is 3. Is 0 equal to 3? No, it's not. Therefore, there is no solution to this system. So the system, which is what they're asking for, I came up with x plus y equals 1. Negative x minus y equals 2. That system will have no solutions. Number 21, create a system of equations with infinite solutions. So infinite solutions, again, you need your x's and your y's to cancel. So maybe I'll say 2x plus 2y equals some number. Now to get the x to cancel, I would want this to be a negative 2x. To get the y to cancel, I would want a negative 2y. And so if we kind of think through where this is heading, if I add these equations together, the x's cancel, the y's cancel, leaving me with 0 equals. Now I need this to be a true statement. So if I have 0 on the left, I need a 0 on the right. So whatever two numbers I put here need to cancel each other out or add up to 0. So maybe I put a 5 here. I'm going to make this a negative 5 there. So 5 plus negative 5 would give me 0. That's a true statement, therefore there are infinite solutions. So just to recap that, what that equation or the system that I just created, we had 2x plus 2y equals 5, negative 2x minus 2y equals negative 5. All right, a solid hour of math. It's probably the best hour of your whole weekend.